For chapter 12, we're moving away from algebra and towards probability. We're going to be looking at how likely it is for events to occur. The first section is about mutually exclusive events. So the first question I had is that if somebody spins a spinner and then picks one card without looking at it, and she gets a 3 on the spinner and the 3 card. Then she sets the card aside, spins again, and draws another card. Is it possible for her to get a 3 on the second spin? Is it possible for her to pick a 3 for the second card? What is the probability of picking a 2 for the second card? So I hope you realize that when you spin a spinner, the number doesn't go away, so it is possible to get a 3 on the second spin. But if she takes a card and puts it aside, so she takes this 3 card and puts it aside, then it's not possible for her to pick a 3 on her second card. And if she puts that 3 card aside, the probability of picking a 2 for the second card would be 2 out of 3 because there are only 3 cards left. These are dependent events. So a vocabulary term, mutually exclusive events are events that cannot occur at the same time. So if you think about drawing a card from a deck of cards, if you choose any card, it's possible that that card could be an ace. But if it's an ace, then it's definitely not a king. So drawing an ace and drawing a king are mutually exclusive events because if you draw just one card, it can't be both an ace and a king. However, if you have drawing a heart, which is a suit, and drawing a king, it is possible to be both of those two things because there's one card, the King of Hearts, that's both a heart and a king. So those are not mutually exclusive events. So an example is if you roll a die just one time, that is, and the two events we're looking at is the event that the roll is an even number, and the other event is the event that the roll is a 3 or a 5. So I'm going to go ahead and list those as a Venn diagram. So if I roll a 1, that is not even, and it's also not a 3 or a 5. If I roll a 2, that is even. If I roll a 3, that's not even, but it is a 3 or a 5. If I roll a 4, that's even, but it's not a 3 or a 5. If I roll a 5, that is a 3 or a 5. And if I roll a 6, that's even. So the probability that I rolled an even number or a 3 or a 5 is 5 out of 6 possibilities. It's everything inside of the Venn diagram. For this is a mutually exclusive event. You can't be both even and a 3 or a 5 because 3 and 5 are both odd. This is the same two events, but this time we're asking the probability that you get an even number and a 3 or a 5, and that probability is 0 out of 6 because there's nothing in this overlap. These are mutually exclusive events. That means the overlap is empty. All right, so here is a second example for you to try. I want you to decide whether this is a mutually exclusive event. If it is, there would be an answer of 0 for the overlap. You can go ahead and pause the video and then restart it after you have tried this problem. This example, because it's a 10-sided die, these events are out of 10. If I look at A or B, there are 7 items that are inside of this Venn diagram. There are 2, 4, 1, 3, 5, 7, and 9 are all either less than 6 or odd. And then if I look at A and B, that's 3 out of 10 because 1, 3, and 5 are all both less than 6 and odd. This is not a mutually exclusive event because the overlap is not empty. Okay, for this example, we're going to be looking at the probability that you land in square A or in square B if you randomly throw a tennis ball at this target. So the target is 20 by 60, so the total area is going to be 1,200 square centimeters. The area of A is going to be 100 square centimeters because it's 10 by 10. And the area of B is also going to be 100 square centimeters. And then the area of the overlap it's a 5 by 5 square, so that's going to be 25 square centimeters. So the probability that it lands inside of A would be 100 out of 1,200. The probability that it lands inside of B would also be 100 out of 1,200. But if I just use those two probabilities, then I've counted this square twice. So in order to fix the problem of counting that square twice, I'm going to subtract that square. So that would be 25 out of 1,200. So because there's some overlap, I have to subtract the overlap so that I don't double count it. If I reduce these fractions, I would have 1/12 plus 1/12 minus, if I reduce this one, I don't have 1/12. So I'd have 2/12 minus something 25 over 120, which would be a nice way of reducing 25 over 1,200 would be, I'm going to divide by 25. So that'd be 1 over $512. How many quarters would that be? That would be 48 quarters. So then if I subtract those, I need a common denominator. So I'd make this a 48. So it'd be 8 minus 1 over 48, or 7/48. So that's the probability that I land either in the yellow or in the blue or in that overlapping area. So just if I'm figuring out the probability of a mutually exclusive event, I don't have to worry about the overlap because there isn't one. So I just add those two probabilities. But if I'm trying to figure out the probability of a non-mutually exclusive event, then I have to subtract the overlap so that I don't count that part twice. Another definition for this section is the complement. That is the set of all the other outcomes, not the ones we're interested in. So if we say that event A is rolling a 5 or a 6, the complement of event A would be all of the other numbers, 1, 2, 3, and 4. An example of a complement would be the probability of spinning a 3 would be 1 out of 4, and the probability of the complement of that would be 3 out of 4 because there are 3 numbers that are not 3. For complement probability just in general, if you're trying to figure out the complement, that would be 1 minus the probability that A does occur, would be that complement probability. All right, that is the first section of Chapter 12. Thank you so much. Good luck.